Today we're going to talk about the activity 321, the asynchronous counters, and the small scale integration here. And we're going to go through the PowerPoint for this. And so here we're going to define what an asynchronous counter is. We're going to use terms called states and modulus. We're going to build them out of D and JK flip-flops. We've already had experience with those in the flip-flop application. And then we're going to explain the asynchronous ripple effect, and then give you some tips on how to design a counter. One of the things about the asynchronous counter, the first flip-flop is the only flip-flop that is externally clocked. And this also becomes your least significant bit of your counter that you're creating. The asynchronous counters are slower. That's because as they ripple through their changes on the next clock pulse, it takes time for it to update. And also this ripple causes some problems. It puts in some extraneous clock pulses. So first of all, we got to determine how high we want to count. And for example, if you want to count up to 7, you would need 2 to the third, which is 8. And really counting up to 7 is actually 8 states because it's 0 through 7. If you wanted to count to 12, 12 requires 4 flip-flops, and 4 flip-flops gives you 16 states, but you still need 4 flip-flops because 12, if you take a look at it as a binary number, is 1, 1, 0, 0. So we actually do need 4 of those flip-flops. And here's one of our basic building elements, and this shouldn't be new to the students. They should be able to take a look at this and say, hey, look at Q knots tied into D. Every time the rising edge, this is a rising edge clock on here, and the rising edge clock is due to, and I didn't get my pen out here, so I need to get my pen on here. Let's see if I can do that. It looks like I'm going to have a little trouble here. All right. Yeah, the rising edge of the clock. Oh, shoot. Let me see if I can get my the PowerPoint pen on here. Huh. I guess it's below my line here. There we go. That's what I wanted. So let me go back to my. Yeah, if you take a look here, the Q naught is tied right back into the D. And then every time we have that rising edge on the clock here, this flip-flop is going to toggle. So the students should recognize this as a toggling flip-flop. And this is our basic building element that we'll use in our counters. If you take a look at our count, I did another video kind of showing the binary count and how the toggling flip-flop becomes a building element of it. And we're going to take a look at that next. The other thing is students should recognize and remember this, like I said, from the applications when we went through D flip-flops and JKs in the previous section. And actually this is a divide by 2 because we have a frequency of 40 Hertz coming in here. And this thing will divide the frequency by 2. So this has got 20 Hertz output right here. So there's actually 20 Hertz here. If we put 40 in, and this is a frequency divider application. And that's a good question on the end of course test. They have a few of those. So, all right, now we want to emulate our first least significant bit right here. That's the one with the clock coming in. So this becomes our LSB. And it toggles every other time with the rising edge of the clock pulse. And what we need to do is we need to get our middle bit, say we're building a 3-bit counter here, we need to get it to toggle every other time. And the way to do that, and I explain it, I think, pretty well in the other video on binary counters and the counting sequence, is we tie the Q naught forward. Right here, we tie Q naught forward, and that gets our second one. And if we take a look at the next slide here, once again, the most significant bit here, we tie Q naught forward to the clock of the next one. And if you look here, this is our most significant bit right here. Of our counter, and they take it and place it right here. This one's our middle bit right here off its Q, and this is our least significant bit. It's the one with the clock that comes into it. And here we have a basic 3-bit counter. If you let this thing just run, count 0 through 7, it'll roll over and repeats again, 0 through 7. So it'll sit there and run forever till you remove power on it. If you notice, all the presets and clears are all tied high, so the flip-flops will work normally with the clocked input for the D. And here's that ripple effect that we were talking about. As the counts change, you can take a look here. Here's the least significant bit. It changes right there. And then there's a little bit of time before the next one wants to change. And then there's a little bit of time before the most significant bit changes. And in there then, sometimes what you'll do is you'll see other counts occurring. So that you get some spurious counts in there before the counter actually goes from one state, which is right here, to the next state. And what they're showing you here is going from 7 rolling over to 0. You actually would see a 6 and a 4 in there. And this is kind of like if you talk to the students about their date of birth, and as they're switching those 3 switches going through count from 0 through 7, sometimes when they change certain switches to go to the next state, they see something pops up on a display that's not in the sequence of month, dash, day, dash, year. And it's the same idea. Obviously there you're going much slower, but this is one of the effects that these counters have, and that's why they call them ripple counters. Now, if you had a 7-segment display hooked on here, you probably wouldn't see this if the clock was running at a decent speed. So if that's okay, it's okay to have them as countdown counters. All right, now we got up counters, we got down counters. So in this case, to make this thing be a down counter, the one thing that they do change is they clock forward the Q. Take the Q to the next state up. So same layout, everything else is the same. We got a counter, counts 7 through 0, then rolls over to 7 and starts repeating again. So pretty straightforward. This is a nice summary page. We haven't talked about JK flip-flops on this side, but if you take a look at the left-hand side of the page here, we have our D flip-flops, and they show you how, if you want an up counter, you tie the Q naught forward, and if you want a down counter in the D flip-flops, you tie Q forward. Now what you have to do is you got to think in reverse logic with the JKs. Now JKs can be counters too, because you can set a JK up in the toggle mode, and the way you do that, that's that 4th state where both J and K are 1. If you tie J and K to 5 volts, tie them high, every time the clock pulse comes in, right here, got your clock pulse coming in, then that JK flip-flop will change state. Now the one thing to notice is one of the more popular JKs to use is this one here with the negative edge. So that would be the falling edge here. And due to that little active low, not symbol, falling edge, in order to do an up counter with JKs, you tie Q ahead. So it's just the opposite as the Ds. Down here, if you want a down counter with a JK, you tie the Q naught forward with it. Good summary slide for the students to go back to if they forget. And here they just build up a JK. You can see here where the J and the K right here are all tied high along with the preset and the clear. That's because these presets and clear are active low. So they have to be tied high so the JK and the clock works normally. But here we have a regular up counter with the JKs. And here we have a down counter, and the only thing changed once again is that they use Q naught for the JKs. All right, now what we're going to do is we're going to take a look at a modulus counter. Now a modulus counter usually doesn't count from 0 to 7 or 7 back to 0. It counts from some count to some number. And we had an example of this if you looked at the random number generator earlier in the year and at dice. And on the dice, the only thing it had to output was it had to output a 1 to a 6. And so we had a little bit of a feedback circuit right here. And they kind of showed it in it, but we didn't go into any details. Next year, if you teach this, you can tell your students we'll talk more about this when you get to counters. Well, here we are at counters, so now we're going to talk about it. What they want you to build this time is they want you to build a counter that the upper limit of the count is 5. So it actually gets to 5. So you see it here, 0, 1, 2, 3, 4, 5. So it gets to 5. And at 5, instead of 7, it rolls back to 0. Goes back to 0 again. And the way it does it with this, and I call this feedback circuitry here. And the one reason they use a NAND gate is a NAND gate has that property where if you have 3 ones as input to it, you get a 0 out. Otherwise, all the other states are high. So it kind of makes it nice for controlling these clears. These clears normally need to be high, except for the time that you want to do something. Well, now in order to do that, you got to get a 1 here and a 1 here and a 1 here to activate this to drop. Whoops, I'm drawing that in the wrong direction. Activate this to go low and clear these all to 0 because we want this to count up to 5, and then as soon as it hits 6, we want to go roll over to 0. So 6, if you take a look at a 6, remember this is the most significant bit, is a 1, 1, 0. And let's take a look at what we're tied to here. We're tied to the Q output, so we get a 1 there. Here, we get tied to the Q output also, it's a 1. But this one, for the least significant bit, trace it back, it goes to Q naught. Well, it goes to Q naught because when this is a 0, this outputs a 0, this outputs a, let's do this here. This outputs a 1, and that's what we need. We need a 1. So now we get our 3 ones. This drops to 0. We clear this back to 0. And you'll see that right here. Here is the count of 6. It's just for a split second. It counts 6 right there. And then NAND gate sees the 6. It generates the reset pulse right there. And now we're counting 0. So that's how this little NAND gate circuit works there. And this is 0 to 5. Now, let's say we wanted to count to 6. Well, what we do is we would actually probably this would be set up to Q here to look for 7. As soon as it hits 7, it would do the reset. The other thing is on that counter that we built, the random number generator counter, it had to start at 1. Well, you don't always have to hook to all the clears. If you want this counter to start at some other count, what you end up doing is you actually disconnect this preset on here, and you disconnect this right here, and you need to tie this high, and this clear line would come up here and tie into the preset. So now when we get a reset signal, this would go to a 0 because of a clear, a 0, and then this would preset to a 1. And like I said, we would have to change this up to Q. Now when it sees a 7, it resets to a 1. So that's how that random number generator circuit was created. And you can go back and reference that. You can pull it up. Remember, you had the diagrams for it on the PowerPoint if the students want to see that. So when you build these asynchronous counters, first of all, you got to determine, are you building an up counter or a down counter? Is it going to be modulus? Means it's going to count to different counts than the full range. Pick your flip-flops. You can build these out of D flip-flops or JKs, and here's the actual part numbers for them if you're building them in the design tab. You can also build them in PLD tab. You got to figure out how many flip-flops you need. Depends on the count you go. And once again, you got to work on what is that reset logic. What are you gonna use for a reset on that? All right, that pretty much ends our presentation here.